This is one of those videos I didn't think I'd have to make. I thought of making it ages ago and thought, nah, there's no need. Surely people aren't that stupid. And then some clown said, hey, it's really interesting that on a steel worktop, bleach disables technically, the virus in like seconds. And wouldn't it be interesting to see whether it also works if you inject it? Dude, yeah, it'll disable the virus. It'll disable everything that's got DNA or RNA in it. It'll kill the patient. Anyway. Epidemiology, what fun. Population of susceptible people. I can write it upside down. Now population, just make sure that's in frame, yes it is, has babies. So the larger this population is, the faster it's going to grow. But obviously, also people die. So way down here we have the ever-growing pool of the dead and gone. The irrelevant, because they're no longer part of anything. What happens when an infectious disease, not a hereditary disease or a UV damaged disease, gets into the population is that someone gets infected, obviously. It's kind of in the definition. Right, being infected, it makes no difference at all for very little time. But the whole definition of an infectious disease includes the fact that people who have become infected are going to become infectious. And that's significant because contact between susceptible and infectious, and the more of these people there are, and it's not just the more of these people there are, it's the more those people come in contact with each other, the more often people move from susceptible to infected. You can be susceptible all your life. If you never meet anyone who's infectious, you don't get infected. Someone who is infectious isn't necessarily going to bump into anyone who's susceptible and infect them. But it generally does happen because people tend to be in contact with each other. Infectious people then become sick. I can draw upside down, I really can. Sick and also infectious. Once they're sick, you actually know you've got an infectious disease running around. Of course, they're still infectious, so they can still contribute to this rate. Sick and infectious become dead. And actually still infectious for a while. But then they become dead and gone. Now, the times here can vary immensely. In the movie Outbreak, this was like 48 hours to here, which is ridiculously fast and terrifying on a local scale, but it's rather easily bottled up. I'll come to that. With something bacterial, this stage could last centuries. With viruses, they're dependent on a host cell. This stage could last hours or days. Because bacteria, they can eat the dead body and reproduce in the dead body, and in the soil around the dead body if it's buried in soil, or in the wood and then in the soil, and remain alive and reproducing and capable of causing infection. So those bodies contribute to this rate. But it's contact with them. Contact between susceptible people and infectious, sick infectious, or dead infectious. Obviously, not everyone who gets infected with any disease is going to die. You also, let's change the arrowheads here to make it distinct. That's movement of people between population groups. You also have movement of people who get infected just get infected or recover. Never even get infectious. People who do become infectious but never actually get sick, they recover. People do get sick, but then they recover. And they will move to a different population group, generally, resistant. Now, these guys, it says these people, these individuals are resistant. They don't get infected. So this is marvellous, because they can have as much contact with this lot as they like. These can get rid of the dead bodies safely. You then have the question of whether resistance is hereditary or not. Generally speaking, it's not. So the resistant population is going to have babies that are susceptible. And of course, resistant people do die of other causes and go to the dead and gone pool. Meaning over time, given a few generations, this pool will disappear, this pool will keep growing. Because they're having babies in this pool and dying. In an outbreak, ideally, what you want is a whole lot of resistant people and nobody susceptible, or no contact with the infectious. Both of which contribute to no contact between susceptible people and the infectious. The original vaccination, the actual word vaccination, comes from this wonderful ability that somebody discovered, that probably several people discovered, but somebody finally formally researched and announced, to move people from susceptible to resistant without them ever getting infected. Without going this way, without any danger of going this way, they can just do that. They can just go that way. The original one was an environmental factor called cowpox, caused by the Vaccinia virus. Vaccinia causes cowpox, obviously in cows. It also infects milkmaids. They get scars or warts or something on their hands from being infected with the cowpox virus, Vaccinia virus. But it doesn't make them particularly sick. It's not a big deal. They get cowpox, they recover from cowpox, they have scars from cowpox. Okay, so you've had cowpox. What's the big deal? It's not a problem. Some milkmaid mentioned that she's not scared of smallpox because she's had cowpox. And she knew full well that milkmaids who've had cowpox don't get smallpox, caused by the variola virus. And this was apparently well known among milkmaids, and some scientists went, "That's very interesting, must investigate that," and did, and found out it's actually true. Taking samples from someone who is infected with cowpox, as a way of getting a sample of cowpox virus, and injecting them into other people, causes them to get cowpox, or a very mild form of cowpox, and then they don't get smallpox. If you inject everybody, well, it's going to be 95% of the people in one town, or one half of one town, with Vaccinia virus, and none in the other half, or in the next town over, and then smallpox comes and goes through the whole region, the people you injected don't get sick. And because you have moved people from here to here, there are very few people here. So no matter how much contact is happening, contact between infectious people and these people is pretty rare, because the infectious people are mostly meeting the resistant. So even those that you missed, even the homeless people, the ones who hid, the ones born since you went through, the ones who've just moved there, the ones who were away at the time, they only ever meet resistant people. They never meet infectious people. They never get infected. That is one way to reduce the rate of infection. You can also reduce the rate of death, of course, right here, hospital treatment. And there is a currently very topical issue. The UK is testing people who are very sick. You'd have to divide this pool into slightly sick and very sick. And the UK is only testing people when they get that far. South Korea is doing its best to identify people at this stage. and is providing hospital treatment for these stages, up to slightly sick, rather than only for the very sick. And hospital treatment, I should have an arrow pointing at this. It increases that and therefore decreases the death rate among people who have been sick enough to get hospitalised, which in the UK is a very small proportion of cases, which is why something like 98% of our confirmed cases are dying. In South Korea it's like 2.6% because they're identifying almost all their cases. They're identifying the people who are going this way rather than only the people who go that way or that way. Right. Other things you can do. Let me just check how long I've got here. I'm on 10 minutes, I've got plenty of time. Other things you can do. When someone gets sick, oh, hey, this person is sick, let's isolate them. You can quarantine the sick. That will reduce this contribution. You don't have to quarantine the infectious dead bodies. You can take precautions with them. I mean, it's easier with a dead body because you don't need to keep it alive anymore. You don't need IVs, you don't need an air supply. You get a couple of these people, just people wearing protective suits, to seal it in an airtight bag, bleach the outside of the bag, problem solved. Talking infectious, people who aren't sick yet, well, if you can identify them, you can isolate them. 3 Blue 1 Brown has a great video simulating an epidemic. It's actually called Simulating an Epidemic, in which he does simulate the effect of identifying and isolating people in these stages. It's quite dramatic. There is, of course, total curfew. And this is why I said that the Mataba virus in outbreak was actually quite easily contained, potentially. See, the Mataba virus, you go from there to there in 48 hours if you're infected. If the Mataba virus gets into a town, nobody goes outside at all. Everybody stay in. Like, I'm not kidding here, if you step outside you get shot. It takes 12 hours for people to start taking it seriously. 48 hours later, anybody who was infected, anybody who made this journey before people started taking it seriously and staying home, is dead. And since people started taking this curfew very, very seriously, because anyone who broke it got shot, very few people have made this journey. The only people who've made this journey are the people sharing a home with the people who were already infectious, which is probably a minority. After 48 hours of actual effective curfew, if there aren't any dead bodies in that house, nobody in that house is infected. And as far as I'm aware, the Mataba virus wasn't transmitted. Oh, it was, wasn't it? It was transmitted via a well. So you would still need to clean up. But you've got 48 hours in which to clean up. 48 hours, you can live without even drinking. And everyone in the town has tap water in that film. You don't need to eat. You can live a week, technically, like 2 or 3 weeks without eating. Odds are, almost everyone's got 48 hours of food. The number of casualties from a 48-hour lockdown is negligible, right? Apart from the people who were already infected and were therefore already going to die because that virus was untreatable, until they pulled the Deus Ex Machina ending. So that works. But the thing that would have made Mataba a whole lot scarier was a 2-week delay right here. Mataba, you get infected, you become infectious, you get sick, you die. Imagine a variation on it. Ebola, for example. You get infected, you become infectious, you get infected a week later. At this stage, it may not even be possible to detect with a test that you're infected. The virus could hide. Eclipse phase. The cells are infected, but that's all. You're not producing virus yet. You're not producing antibodies to it in large enough amounts to be detected. It's just lurking. Then you get infectious, and you spend 2 or 3 weeks infectious before you get sick. Well, that's 2 or 3 weeks in which you can do an awful lot of travelling, go to work and back, go visit your relatives at the weekend. If you're a journalist, complete your assignment in country, fly to Heathrow Airport, get on the tube train on the Northern Line to King's Cross, change to East Coast Main Line up to Leeds and go and report to your office in Leeds and file all your photographs and video and all your news articles. You could infect an awful lot of people in that time. So Mataba, a lot easier to contain than some. Now, if you want a way to make this, another way to make Mataba a whole lot scarier, it's right there in Mataba, it's right there in the current problem. It's whichever origin story you believe, whether you think people living near caves that had bat populations came in contact with bat guano or bats and got infected, or it came via chickens, pangolins, rabbits, pigs, whatever, a live market, or people at a lab studying the people who got infected from living near the caves had an accident and got infected, or people in a lab studying a way to weaponize it had an accident and let it loose. All the possible origin stories include bats and or chickens and or pigs and or pangolins and or raccoons. Mataba, origin story, includes that monkey, right? All of these are human. But right here we have a susceptible population that can get infected and become infectious and get sick and become dead but still infectious and then become dead and gone. That can happen, and of course they can recover and become resistant from any of those 3 stages. And of course, they naturally die, and the resistant ones naturally die, and the population is reproducing, and that population is reproducing. That's fine. Exactly the same situation, and the infectious dead, or the infectious sick, or the infectious not yet sick, can all contribute, coming into contact with the susceptible, can all contribute to the rate at which susceptible individuals become infected. Now, if it's something like cowpox, in theory, in theory, you've got this vague possibility of environmental factor, kind of an accidental vaccination. The big scary part is that this central line is shared. Contact between a sick infected raccoon, bat, pig, pigeon, chicken, whatever, and a susceptible bat, chicken, duck, goose, rabbit, human, can cause the susceptible human to become infected. Contact between an infectious but not yet sick human and a susceptible cat can cause the cat to become infected. It then becomes infectious and then infects another human, because a lot of domestic cats are allowed out and they actually have several human families. They go around for 3 breakfasts, 2 lunches and 3 dinners. So it could jump from house to house via a cat that has 2 houses, or via bats or raccoons. Once you have these other species, you have the possibility that infectious human who's self-isolating, doesn't know he's not sick, doesn't know he's infected, but he suspects he might be, he's just being socially sensible and self-isolating, puts out the rubbish. A susceptible raccoon goes through the rubbish and gets infected. That raccoon spreads virus, becomes infectious, spreads virus, and somehow infects a rat. The rat's going through the raccoon's leftovers or something, or at another bin or whatever. The raccoon shits out infectious virus particles. The rat walks in them and gets infected. You then have a susceptible rat that's become infectious, and that infectious rat raids the kitchens at the old folks' home and contaminates them, and suddenly 80 people in an old people's home on the far side of town from this infectious guy have all been exposed, and 60 of them become infected. And because they're all old, like, one will recover and 59 will become infectious, and one will recover and 58 will get sick, and I think it's 80% mortality rate among the over 80s. So yeah, roughly 50 are going to die, because it also infects raccoons and rats. Or pigeons. So here's a question for you. How exactly do you go about quarantining sick rats? Or pigeons? How do you impose a curfew on rats? How do you vaccinate all the rats? Well, you can vaccinate wild animals against some things. We have oral rabies vaccine baits. It's a block of food, a bit of chicken liver pate or whatever, suet, tasty snack with a rabies vaccine in it. You just fly low over the forest and toss the things out of the window. And you just hope that most of the foxes or raccoons or wolves or whatever are out there will find and eat these baits and become vaccinated, which makes most of the susceptible ones resistant and reduces the spread. In terms of the spread, it is this rate, this rate and the sum of these rates compared will tell you how fast this population is growing. If you have susceptible individuals becoming infected more rapidly, more often, rapidly is correct, than the various infected people are recovering or dying, then this population is growing. If they are becoming infected less often than they are leaving this population, one way or another, this population size is shrinking. There's a number we use to measure this, which is the reproductive number. And we have various values for this for various known infectious diseases. I think it's 13 for measles, which is just terrifying. 2 for the flu. The R0, which is to say the reproductive number when 0 of the population are resistant, everyone is susceptible, is the number of susceptible individuals who will become infected as a result of contact with infectious, sick infectious or dead infectious for each person who becomes infected. So 1,000 people become infected, some recover without ever becoming infectious, some become infectious and recover, some become sick and recover, some become sick and die. Those 1,000 people, because they come into contact with more susceptible people, they create 1,010 new infections. Your reproductive number for that iteration is 1.01. It's more than 1, and this population is growing. If they only infect 998, then it's 0.998, and this population is shrinking. If you can keep it below 1, that disease is eventually going to go away. If it stays above 1, as long as it stays above 1, that disease is spreading, more and more people are getting infected, and your active case count is going up. Which brings us to hospital. Say you have a population of 80 million, because you're Germany, 65 million for the UK, 300 million for the US, whatever, 80 million people, and you have enough hospital capacity to treat 100,000 sick individuals. If this spread is slow enough that the active number of cases never exceeds 90,000, then you might have to move a few patients from hospital to hospital to put them where there's capacity for them, but everyone gets treated. If it goes to 110,000, that's 10,000 people you can't treat. There's 10,000 people where you have to make a choice. You have to say either, you guys are young and healthy, you'll probably recover from this even without our help, we're going to treat the old people over there, the guy with a pre-existing condition, pregnant lady, the infected healthcare workers, that's a serious issue, because they're more important, infected healthcare workers, we need them. It doesn't matter having 100,000 hospital beds if we've only got 1,000 nurses. They can't treat 100 patients each. We need the medical staff, so we're going to treat them, not the unemployed. Or you do go the opposite way when you still treat the medical staff. You can say, you know, we're going to treat the people who are most likely to die without our help, or you can say, these guys are likely to die even with our help, so we're not going to bother treating the elderly, we're going to treat the young who have the best chance of survival with our help. Or you try to assess where your hospital help is going to make the most difference to the chance of survival and divert the most people from that path to that path. But you can't treat everyone. So keeping this population small, really good idea. Keeping this population small is a really good idea for very similar reasons. Not that you're trying to treat them in hospital, but that the larger this population gets, the greater the contribution they make to this movement rate. And you can't really treat these in hospital, but the fewer of these there are, the less they contribute to that, the less rapidly people are moving from there to there, and the less rapidly this population is growing, less likely your hospital capacity is to get overwhelmed. So have I got time to talk about contact? I have less than 2 minutes. Contact. In the case of cholera, this contact. Cholera is a bacterial disease caused by Vibrio cholerae, which causes massive amounts of watery diarrhea. People die of nutrient loss, dehydration, actually salt loss, just because so much is coming out of their arses rather than, you know, being part of their own supply of resources. The way to treat it is to feed them large amounts of boiled and very slightly salty water to keep them hydrated and keep their salt levels at a healthy level until they recover naturally. But the whole time that this is going on, generally speaking, cholera outbreaks happen in places where you have poor sanitation. I've heard of a case where the plumbing in a block of flats was so bad, I don't know if it was actually cholera, I don't know what the disease was, but people got infected by drinking water from their taps because somebody else in the same building had an infectious disease and it was going into their toilet bowl. That's a bad situation. Cholera gets into rivers. Poor sanitation, people shit, the shit goes into the river untreated, live cholera bacteria go down the river and get ingested downriver by people who didn't boil the water. So one way to fight a cholera epidemic, one way to reduce this contact, is to provide sterilisation of water. Sterilising the water, UV treatment, boiling it, any of a lot of ways of sterilising the water won't destroy the cholera toxin, it won't stop it giving you the shits, but it will stop cholera, kill the bacteria, prevent them actually infecting new people. And I'm about to have to stop recording. Yeah, 1 minute left. Part 2 coming soon.